No, actually, I guess it has to be J. Sorry. J is less. Anyway, so if we have these extra paths, so if we have more than one path between two vertices, we just delete all but one of those paths. So here we would concatenate these two guys, end up with a cycle there, and we delete all but one path. Okay. And so this descending star network is just anything you get by doing this. So collection of stars. Okay. And a path family on a planar network is a collection of source-to-sink paths in the planar network. So you've got n source-to-sink paths, so that each source in sync lies in exactly one of the paths. So you just have, for every source, you have a path to some sink. And they're all distinct. We say that a path family has type W if there's a path from Si to TWI for all I. Where by W sub I, I mean W of I. Okay. So, again, the path matrix here is defined exactly in the same way as I defined it on the chalkboard. So it just records whether or not. So you notice that in a descending star network, there's either 0 or 1 path from any source to any sink. So this path matrix in this case is always just a 0-1 matrix, recording whether or not there is a path from any source to the corresponding sink. Okay, and so to evaluate our immanents on these tableaux, we're going to need to introduce combinatorial objects called F tableau. So an F tableau of shape lambda is a filling of a Young diagram of shape lambda with the paths in some path family on F. So a Young diagram of shape lambda is just you have a row of length lambda I for each element of the partition, each number in the partition. So a couple examples here. So here's some planar network, same one we were just looking at actually, and here I've chosen a path family on it given by these 4 paths that I colored in. So again, there's always going to be exactly one path going to every source in sync. And then we can just start, well, I gave them all names so that I can put them in the tableau. And then we just start filling tableau with these paths. So here, if lambda equals 4, then the Young diagram is just a single row of length 4, and we take these paths and put them into that diagram however we want. Lambda is 3, 1, and then we got a row of length 3 and a row of length 1. That's all we're talking about here when I say F tableau. An inversion in an F tableau seems like fairly obvious, but so a pair of paths pi I and pi j in a tableau are going to be called an inversion if they're out of order. So this first thing says they're out of order with respect to sinks, and by out of order with respect to sinks I mean horizontally. So we don't care where they are vertically in the tableau, but the path with the greater sink is appearing horizontally before the path with the lower sink. And furthermore, to count as an inversion, we require that those two paths intersect in the planar network. Okay, and then we say that n of t is the number of inversions in the tableau. So let's look at some examples of that. So how many inversions are there in this tableau where I labeled the paths by colors here so you can tell what they are. So I guess I labeled them by their source vertex. So let's see, how many inversions are there in this tableau? Well, 2 and 1, they're appearing in order with respect to their sinks. 2 and 4, remember we don't care where they are vertically. Also in order, 3 and 4 also in order, 3 and 1, out of order with respect to their sinks. But those paths don't intersect, so that doesn't count as an inversion, so there's no inversions in this tableau. Let's see, let's look at the next one. Paths 1 and 2 here, they appear in the tableau out of order with respect to their sinks, and they do intersect, so that's an inversion. 3 and 2 also out of order, also intersect, that's 2 inversions. 4 and 2 also out of order, but don't intersect, so there's 2 inversions in that tableau. And so on. Again, key takeaway here is we don't care whether they are vertically, only horizontally.
So they don't have to be increasing, but increasing. Every possible filling is legal?
We're going to start disallowing them soon.
But right now?
Right now they're all yeah.
Sorry, what was it? You said 2 and 3 are out of order?
In this tableau? Yeah.
But their 6 are in the right order? No?
So 3 is to the left of 2, but the sync that 3 goes to is above the sync.
Oh,
that 2
it's
goes
just
to.
they have to differ in that sense.
Yeah, just above.
From where they are.
Yeah.
Gotcha.
So this one, the guy to the left is above the guy to the right. You say they're out of order,
Okay.
which is sort of what I wrote up here, but I was confused with those indices. Right. Oh, so a few more examples here. I have another planar network and some more tableau, which I again labeled by their sources. So I again labeled all the paths by their sources. And so I guess I just wanted to emphasize by this example that like the sources don't determine the inversions. And furthermore, just the tableau of sinks doesn't determine the inversions either because it depends on whether things intersect or not. So here we get totally different numbers of inversions for a bunch of paths arranged in the same tableau with respect to their sources. But I guess you can go through an example now. Like for example, in this tableau, 1 and 2 are in order, 3 and 2 are out of order, 4 and 2 are in order. Yeah, but here nothing intersects anything except for 4, so actually really the only pair we have to look at is 4 and 2, and they're appearing in order. Yeah, so I guess we could look at this one. Again, we really only have to look at wherever 4 is. Here it's out of order with respect to 2 and 1, so you get 2 inversions. Okay, so that's how we count inversions in Tableau. All right, so this is sort of the main result right here that the other results are going to come from. And that is that if F is a descending star network, and we have some pair of permutations, then we can evaluate the monomial in the matrix, quantum matrix algebra corresponding to those permutations as follows. We say that if we have paths from the sources given by V to the sinks given by W, so these are permutations when V is less than W in the Brouillard order, then, so if we have all these paths, then define this tableau to be, define this tableau TFBW to be just a one-row tableau where we put all those paths in order. And then our evaluation works by just evaluate this monomial, xBW times power qBW, evaluate that on A, and we're just going to get Q to the number of inversions in this tableau. And if we didn't have all those paths, then the evaluation will be 0 because we'll have 0 entry. So that's sort of the main result, which we can now use to get some other results. I'm not going to prove this. Okay, so to actually evaluate the immanence that I defined, we're going to have to talk about certain classes of F-tableau. So we say that a tableau is row closed if the set of source and sink indices in each row are identical. And we say that it's canonical if the paths are sorted in each row with respect to their sources. So here, this guy, is this row closed? Well, let's look at this row. The source here is 1, the sink here is 2, the source here is 2, the sink here is 1. Those are the same set. So this row is closed, and there's only one other row, so it also has to be closed. So this guy is row closed. Is it canonical? Well, this row is sorted by source order, and this row is also sorted by source order, so yes, it's canonical. Is this guy row closed? Well, we can immediately see it isn't because this row uses sink, so source 2 and sink 1, and 2 is not the same as 1. It is our canonical because there's only one non-trivial row there, and those paths are in order according to their sources, and so on. let's see. Oh, here, an example of something that's not canonical because these guys are appearing out of order with respect to their same sources, rather. Okay. More special kinds of F tableau. We say that an F tableau is row strict or column strict if every adjacent pair in the row or column is in order according to the, well, both the sources and the sinks. So the path to the left of or below has to lie entirely below the path to the right or above in the tableau. And semi-strict if we allow them to intersect. So let's see. This tableau here is column strict. It is? Okay, so let's check. Path 1 lies entirely below path 3. And path 2 lies entirely below path 4, no intersection. So yeah, this guy is column strict. On the other hand, it's not row strict because 1 and 2 intersect. It is row semi-strict, even though these guys are sort of out of order, but these guys intersect, and these guys also intersect, so it's row semi-strict. Let's see, here's an example of something. This is column strict because path 1 lies entirely below path 3, but it's not even row semi-strict because path 4 lies entirely above path 2. And here I wanted to point out, so we really care only about adjacent pairs, right? So here, path 3 lies entirely above path 1. That's okay because they're not next to each other. So this guy still ends up being row semi-strict. Okay, so those are all the tableau we need to worry about. Here we can give the results. Well, we need one little definition here. We're going to define the flattening of a tableau to be the tableau given by taking your original tableau T and putting all the rows next to each other. So if we take this guy and flatten it, we'll just take 3 and put it down here, and 4, put it down there, and end up with 1, 2, 3, 4. And the same thing would happen to this tableau. We take this row, put it here, and we get 1, 2, 3, 4. Okay. So if F is a descending star network with, sorry, forget this line. So if F is a descending star network, we have this formula. The eta immanent, eta lim immanent evaluated on the path matrix of F is just the sum over all the canonical row closed F tableau of shape lambda of Q to the number of inversions in the flattened version of this tableau, flattening of that tableau. So that's main result number 1. So maybe I give an idea of the proof. So we expand the immanent like this. All the monomials in that expansion are given by those row-closed canonical tableau. And then we use that formula that I gave several slides ago, to evaluate each of those monomials. So suppose that our tableau is just this single star. And we want to evaluate the eta immanent on its path matrix. Well, first we break this guy up into its sum of products of permanents. So this is sort of like going through how the proof works. Putting some of the products of permanents, and then just taking a sort of random example of one of these guys. Well, here's one of them. We have q to the 1/2 times x13, x31, x22. Well, remember that we defined this guy by saying extend linearly, so it's linear. So when we evaluate this monomial on the tableau, or on the matrix rather, we get the formula. From the earlier formula, we know that this is equal to the number of inversions in this flat tableau, which is the same thing as the flattening of this tableau, which corresponds in a natural way. The set of all these tableaux correspond in a natural way to all these monomials. So that's sort of a sketchy idea of how the proof would work, but it's the idea. Okay, we got one of our families of immanents. The second one is the epsilon immanents. And to evaluate them, we have a similar formula. But here we're summing over the row closed, row strict F tableau, so where they're semi-strict. And row. And
What is that T to the T?
And by little t, I just mean transpose. So here, instead of flattening the tableau, we transpose them. And the proof is kind of like the other one, except we have all these signs, and so we do some combinatorics there to get everything to cancel. So I think going through this long example, here we can just kind of skip straight to these evaluations. So I was going to sort of give a connection to evaluating characters of certain algebra elements, but so here we can just say to evaluate the immanent corresponding to this guy on the path matrix of the planar network here. Well, we need to look at all the tableau we could make out of this planar network, which I've sort of listed here. And then we need to figure out whether they're row strict, figure out how many inversions there are, and all of them flattened to do the eta immanent. And if they are row strict, we're going to need to know how many inversions are on the transpose to do the epsilon immanent. So then to evaluate the immanence, we just get these numbers here. So evaluating the eta immanent on the path matrix of that planar network from the last slide, we'll get, well, these are the tableau of shape 3. Sorry, I only listed the ones that are row closed and canonical. And then, so the immanent, remember, is the sum over all these tableaux, the number of inversions in the flat version of the tableau, which is the same thing as the tableau itself. So it's like q to the 0 plus q to the 1 plus q to the 1 plus q squared. So it's going to, yes, in fact, that immanent evaluated on that matrix would be q squared plus 2q plus 1. And there are no row strict tableau of that shape, so the epsilon immanent would just be 0. And down here, again, here are all of the canonical row closed tableau of shape 2-1 for that planar network. And here's the number of inversions in them. And in fact, the immanent evaluated on the matrix, it comes out to be the polynomial given by q to the number of the sum of q to the number of inversions for each of these tableaux. And here we actually do finally have a row strict tableau, so our epsilon immanent would be q to the number of inversions of the transpose of this tableau, which is just 1, so the epsilon immanent is just q. So that's a sort of example of how this actually works. And that is all. Thank you.